So the fourth talk is titled SWIS Shared Weight Bit Sparsity for Efficient Neural Network Acceleration, presented by Shurui Lee, who is a PhD student at the Department of Electrical and Computer Engineering at UCLA. And Shurui's research focuses on low power machine learning architectures and optical machine learning systems.
Thank you for the introduction. I'm very happy to have the opportunity to present the work I did with my co-authors here. I want to present our quantization framework SWIS, abbreviation of shared weight bit sparsity for efficient neural network acceleration. First, I want to briefly talk about why we need quantization. Nowadays, there is increased demand for deep learning on low-power edge devices, which usually have limited resources. On the other hand, state-of-the-art DNA model size continuously increases. So the model have to be compressed to execute on edge devices. And even 8-bit might not be good enough for some use cases. There exist many quantization and compression techniques. However, most of them cannot be efficiently implemented by edge devices due to lack of hardware support. Thus, we present SWIS quantization framework, which combines both algorithm and hardware. Now I want to talk about bit sparsity, which is the main idea behind the SWIS quantization framework. On average, at least half of the bits for a given weight are 0 for deep neural networks. And the 50% is actually a conservative estimation, since most weights and activations are normally distributed and centered around 0. The more significant bits have higher probability of being 0, and the overall probability actually slightly higher than 50%. And this property also holds true regardless of the precision of the network. So the question is, can we get rid of the 0 bits and only store and compute the non-0 bits? We could do that by performing the computation 1 bit at a time so that we can skip the zeros. In this case, naively, for each non-zero bit, we need to store its index, which is a 3-bit for an 8-bit number. This means we don't have any compression if there's more than 2 non-zero bits. However, we can do better than this, and we use 2 techniques to achieve real compression. The first technique is reducing the number of non-zero bits by allowing quantization error. Since weights can be quantized offline, the quantization can have very high granularity and introduce minimum quantization error. So for the illustrated example here, the number of active bits is reduced from 4 to just 2 by quantization. And we call the non-zero bits after quantization active bits, since they will be actively executed by the hardware. This results in less storage, but it's still not good enough for meaningful compression, since each active bit still requires a 3-bit index. And this overhead is quite large. So we have the second technique to reduce the overhead of the active bits by grouping the weights. The idea is that for n consecutive weights, we group them to share the same active bits, so that their indexes for the active bits can also be shared. But we also want different ways to choose whether to use a particular active bit or not. So we need a 1-bit mask for each active bit of each weight in the group. So in the example I show here, the 4 weights are constrained to share the same 4 active bits, and each weight can still represent different values due to the existing of mask bits. So the bits with a 0 mask will not be computed by the hardware. Sharing the active bits also implies that the underlying hardware that performs the computation can also be shared for the entire group. And I will talk about this later. So what do we need to store exactly? Assume the group size is n and there's n active bits. And with a bit width of b, there are 3 kinds of information that need to be stored. The first one is the index bits, which requires log2b times n bits in total, since we need 1 set per group. And for 8-bit weight, it's 3 n bits. The next is the mouse bits, and we need n bits per weight, so that the total is n times m bits for a group. Lastly, we also need one sign bit per weight, which means n in total, since we process using sign magnitude format. The formula is shown here, and in short, the compression ratio scales with the group size, and the upper bound will be n over n plus 1. And the figure on the right shows the computed compression ratio for different group sizes and number of active bits. The compression is better for a large group size and small number of active bits, which is expected. And for example, for group size of 4, the compression ratio is up to 2.9x for SWIS. So we have already went through the compression and the quantization scheme. And now let's talk about the hardware for SWIS. One way to support such quantization is using bit serial multiplier, which processes multiplication in a serial manner and 1 bit at a time. Doing so, the zeros can be skipped and multiplication can be performed by a single bit shifter, and which essentially trades latency for area and power. As the bit shifter is just shifting bits, they require far less power compared to a normal 8-bit multiplier. But on the other hand, they require more cycles to finish the computation. As shown in the figure, one operand is transformed into a serial bit stream, and the multiplication can be implemented by repeatedly shifting the other operand and accumulate. For n-bit multiplication, it requires n cycles to finish the execution. If all the bits are processed for an n-bit number, bit serial multipliers have trouble to get any benefit compared to normal fixed point multiplier due to the latency overhead. However, SWIS can aggressively compress the weights, so only a very small portion of the bits needs to be processed, and results in better performance and efficiency. So now let's talk about the SWIS processing element and architecture. So individual PE process n weights in parallel since we group the weights to share the active bits. And each group requires m cycles to finish the computation for m active bits. Since the active bits are shared, an entire group only needs a single bit shifter if we reverse the order of multiplication and addition. For SWIS, we have two hardware configurations. One is SWIS single shift, or SWIS SS for short, which is only using a single bit shifter for each group. On the other hand, we also have a SWIS double shift version, or SWIS DS for short, where 2 bit shifters are used for each group and process 2 active bits in parallel to reduce the number of cycles. SWIS DS has better hardware efficiency, but it has the constraint that only even number of active bits can be used since 2 bits are processed at the same time. However, we do have a solution to allow non-even number of active bits on average for SWIS DS, and we'll talk about this later. On the architecture side, we adopt systolic array architecture and output stationary data flow so that it can act as a gem engine. The activation and weights are grouped as shown in the bottom left figure, and they also move between PEs in groups for systolic array operation. Having said that, SWIS is not tied to systolic array, and it can be applied to almost any architecture and data flow. It can potentially achieve better efficiency due to higher scheduling flexibility and less buffer overhead on architectures other than systolic arrays. And so here's an animation of how SWIS computation is actually executed on the systolic array. So for each systolic array cycle, which computes a multiplication for each PE, there are sub-iterations for the PE to iterate through all the active bits since they adopt bit serial processing. And the IG here stands for input group, and FG is filter weight group. S is the number of the current active bits that is being processed. And the rows are activations and columns are filter weights. So here shows the cycle 0 and the computation is about to start. Now we enter the first cycle and the input and filter weights are shifted into the first P to start processing. And the system will process the first active bits. For the second cycle, the system is processing the second active bits and is still inside the bit 0 iterations. So the weights and activations are not passed to adjacent P's for this cycle. And now system is processing the third active bits and in the third cycle. And afterwards, the entire multiplication will be completed, and the system is ready to enter the next systolic array cycle. So here for cycle 4, the system enters the second systolic array cycle, and the activations and the weights groups are passed to the adjacent P's for the next cycle's computation. And we basically repeat the same procedure as the first cycles, and we compute the second active bit, and now we compute the third active bit, and we finish the second systolic array cycle. And then the system repeat again and enters the third systolic array cycle. To avoid scheduling issues, all the filter weights scheduled to the systolic array at the same time should have the same number of active bits. And now I want to talk about the SWIS scheduling, which optimizes the weight quantization and scheduling. Filters that schedule at the same time needs to have same number of active bits, but the filters not scheduled at the same time can have different number of active bits. Practically, not all filters are equally susceptible to quantization. So we can assign different number of active bits for filters to reduce overall quantization error while keeping the average number of active bits same for each layer. For example, here, there are 12 filters in total, and each 4 filters will be scheduled to the systolic array at the same time. Instead of letting all 12 filters using 3 active bits, the scheduling algorithm can let 4 of them using 2 active bits and 4 of them using 4 active bits, if that requires reduce the overall quantization error. So doing so, the network accuracy is improved while maintaining the same number of active bits on average. Moreover, the scheduling algorithm also allows odd number of active bits on average for SWIS double shift version, and non-integer active bits for SWIS in general. So here shows the accuracy result for direct quantization. One goal of SWIS is that given a trained 8-bit network, SWIS can further compress it without training and without much accuracy drop. So the group size is set to 4 for the results, which we find out to be a good trade-off between performance and accuracy. However, optimal group size might not be 4 for some cases, and it depends on user's target. For Resident 18 on ImageNet, the accuracy is higher than 67.5% for all SWIS configurations, using an average of 2.5 active bits. However, for the harder to quantize MobileNet v2, SWIS need at least 3.5 active bits on average to achieve accuracy higher than 65%. And here is the result for SWIS hardware performance for direct quantization. Compared to the ISO area 8-bit fixed point for Resident 18 on ImageNet and within 1% percentage point accuracy drop, SWIS achieves up to 1.37x and 1.23x in frames per joule and frames per second. For MobileNet v2 and within 2 percentage point accuracy drop, SWIS achieves up to 1.25x and 1.31x in frames per joule and frames per second. We also benchmarked on VGG16 on C400, and SWIS achieves up to 1.46x and 2x in frames per joule and frames per second within 1 percentage point accuracy drop. The efficiency advantage comes from the reduced bit 0 cycles, as well as the reduction of DRAM access energy due to the weight compression. The smaller improvement for MobileNet is due to it requires small active bits for direct quantization, since it's harder to quantize, as shown in the previous slides. And this can be improved by retraining to achieve a smaller number of active bits. All the results here are roughly ISO accuracy with 8-bit fixed point. And users always have the option to further improve the efficiency by allowing more accuracy drop. Finally, I want to present some results if retraining is allowed. So if we can retrain, SWIS can further compress the weights and achieve better accuracy. This is especially useful for MobileNet V2 case. And after retraining, a less than 3 percentage point accuracy drop can be achieved with just 2 active bits for MobileNet V2. For Ryzen 18, 2 active bits gives less than 1.5 percentage point accuracy drop. Even with retraining, SWIS framework still maintains its accuracy advantage over layer-wise weight truncation method. And the performance and power efficiency for SWIS can also be improved by retraining. And thank you. That's the end of my presentation, and I'm happy to answer any questions.
Thank you, Shurui. It's a very great talk, and floor is open for questions. Right. So I have one question. The SWIS framework is applied after post-training, right? So you take the model and then...
Yes, it's mainly targeting for post-training quantization.
Okay.
And if like the accuracy is not desired, and if you have the privilege to access the dataset, you can choose to retrain the network and achieve even better accuracy and performance.
Right. And the framework is software-based, which you can basically add it to an existing framework.
Yeah, so it's a mix of software and hardware. So we have our own hardware, which uses through multipliers, and we have our software to generate the weights we need for our hardware.
All right, I'm just saying for the user wants to use it. So you have you take them, for example, floating point or an unoptimized quantized model from TensorFlow or Keras.
Yes.
Format your framework.
Yes. So our framework only requires weight as input, so
exactly.
It doesn't require anything else, and we can do the compression and execute on the hardware.
All right, sounds good. So I don't see any additional questions in the floor. So well, thank you again. We can move to the 5th talk.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Hymax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, Edge Cortex, Hotg, and Synsense.